For example, do your results in numerical analysis. They are being used. I mean, have you done some numerics before? Integration, quadrature.
ये results ने use किए थे कि
You're going to see this code. This is basically very useful when you are doing numerical analysis. Because what does it basically helps us? It's just saying that okay, if you know the function, a little bit about the function, the integrability is guaranteed. Okay. So consider a partition P, which is x naught xn, x naught is A and xn is B, and it's not an arbitrary partition, but it's a cleverly chosen partition such that when you compute delta alpha I, okay, so it's like such that delta alpha, which is alpha of xi minus alpha of xi minus 1, is a fixed number. It's a fixed number. And that fixed number is alpha of b minus alpha of a over n, where n will be chosen later. Where n will be chosen. So I will basically cleverly choose n in such a way that I can have the control that I want to have. Okay. So in other words, it's a partition for which this increment is a fixed number, which is this amount. And n is also fixed, but we'll choose it later. Okay. My claim is this, that then this is also. Now, as f is monotonically increasing, so that on each subinterval xi and xi minus 1, what would be mi? What would be mi? Mi is the infimum of f of x, where x is between xi and xi minus 1. What would be mi? So keep in view that f is monotonically increasing.
It would be
constant number.
It would be constant, but which number?
f of xi minus 1.
Exactly, it's going to be f of xi minus 1. In other words, the smallest, since the function is increasing, the smallest value that it will, like I minus 1 here, I here, the smallest value that function is going to achieve is the left hand point, and the greatest value that it can achieve is right hand point. Otherwise, capital mi is f of xi on each of this.
Minus 1.
So this is also fixed type. It's not a variable. Not
Capital MR xi होगा ना minus 1.
xi होगा.
sorry. If this is the case, then consider you have the alpha and LFD alpha. What would be that by definition? So this difference is going to be equal to the sum, which runs from 1 to n, capital Mi minus small mi multiplied by delta alpha I. Great. this is the case, then can you see that where we are going? So what is delta alpha I?
It's equal to alpha b minus alpha a upon
It's basically this fixed number. I can substitute it here and there is no index here. So I can put it out of somewhere. So I'm going to say that this is equal to alpha of b minus alpha of a over n
times the sum.
times the sum. I equal to 1 to n.
Capital is R is small.
Capital Mi minus small mi. So what do you think what this sum would be then?
B minus A.
It's going to be b minus a.
F of B minus F
F of b minus f of a. Just think about it. Why this would be the case?
Telescopic sum.
It's not by definition, but just think about it. The first thing is m1 minus m1. So m1 minus
M1 plus M2 minus M2
minus
small M2.
small m2, so on and so forth. Now just think about it. What is small m1? So this is minus f of x naught.
F of A or F of
Okay, this is f of x naught. And what is this guy? This is f of x1.
1.
And what is this guy?
F of X2.
That is f of x2 minus what is this guy?
F of X1.
This is f of x1. Because just think about it, on x2 to x, x1 to x2, okay, you have this. Right? So you keep on doing it, just think about it. This guy would be cancelled. This guy would be cancelled. The next guy, and so on and so forth. So this is going to be a telescopic sum. And this is going to be alpha of e minus alpha of a over n times f of b minus f of a. Okay?
Only given table.
Huh?
Given table.
They are images.
Images है ना बेटा. Images है ना. Why this is not to be images? Yes. So f of b है. F of b because
It's
x
not included.
x naught is a and xn is b. So now I have so now here comes what you say the role of this capital M. So I want to make this guy smaller than epsilon. That's what my task is. That's what my task is. Now I don't have control over alpha of b minus alpha of a because this was something given to me. It's not I have chosen. And I don't have control over f of b minus f of a because the function is given to me. I don't have control over it. So I have only control over n. So question is, what should I choose in such a way that this guy becomes smaller than epsilon? So choose So choose n's in such a way, okay,
It's not by this product.
epsilon of this product what?
This product by epsilon.
Alpha
Give me the number.
n is equal.
Give me the number. And bigger than or equal to, smaller than or equal to what? Okay, so I want this to be smaller than epsilon. So I need to throw this on the other side, and I need to throw this on the other side. N is bigger than. Which number of options?
Epsilon by
Epsilon by then epsilon.
Give me concrete numbers. Okay, don't tell me that this number by this
alpha B minus alpha B.
Huh?
Alpha B minus alpha B.
Okay, alpha of B minus alpha of A
Alpha B minus
into f of B minus f of A
Oh, yeah, epsilon.
divided by epsilon. So that's a concrete number, that's a concrete number, that's a number. So for given these numbers, just think about it. When I am beginning to solve a problem, I have these numbers with me already because I know the interval A to B, I know my function and I know my alpha. So this is something in the beginning, I know in the beginning. So in other words, I can compute this and I can choose n, and that n will work out. Okay. Hence, for this choice of n, you're going to have LFP alpha and LFP alpha smaller than this. Okay? Does it make sense? What do you say of really basic conditions? I would like to just mention this result without proof. I'm not going to prove it. So if you wish, you can have a look at it. Which is going to show that, okay, you have continuous functions here in R alpha, and you have these monotonic functions in R alpha, but there are things which are here. Okay? There are things which are. Okay. It's an interesting result. I don't have time to get into that. Okay. It's a readable proof. You can read it for yourself. It says suppose F is bounded. Boundedness is necessary. There is no escape from it. Suppose F is bounded. Okay, one of the things that I like to mention, since these results are true for Riemann-Stieltjes integral, so they are true for Riemann integral as well. Okay. Suppose F is bounded on A comma B, that's and as finitely discontinuities if alpha is continuous all points where F is discontinuous, then F belongs to Something very interesting. Think about it.
Remove that. Continue.
No, you're not removing anything out of it. You're not making any change in it. So I'm saying that f is a function which must be bounded, obviously. Second thing, it has only finitely many discontinuities. But at those discontinuities, your alpha, we need that alpha must be continuous. It shouldn't be. So it's like f and alpha should not be both discontinuous at finite terms. So in other words, alpha must be, alpha is monotone, but it's continuous at those points where f is discontinuous. So if this is the case, so let's just assume it bounded this. The next thing that I would like to move on is basically what we say the elementary properties of integrals actually. Okay, so we see lots of properties of integrals, but we want to prove them by definition. After this result, we should can get more results.
Password.
Which says that if you take f1 and f2 from R of alpha, in other words, if they are integrable with respect to alpha, then
There's some also are
their sum is also in R of alpha. This would be interesting because this will turn this space into a vector space.
Scalar matrix.
But you need also scalar and scalar. But that is true also. So it's like if two functions are integrable with respect to alpha, then their sum must be, integrable with respect to alpha. Question: what would be the integral of this sum? You can ask. If it is integrable, then there must be some integral of this sum actually. And we know that this got true as per our expectation that the integral of this sum is basically the sum of
it.
some of
the alpha.
direct alone. Like that.
This identity is answering a question that that you want to find the integral of this sum, just take the sum of the integrals and you're gonna get this. That's one part, part A for this problem. Part B of this problem is that this integral, the Riemann integral is a monotone function. If I treat that as a function, so in other words, if I define a map from R of alpha into R, just making sense of that, T of f is integral of a to b f d alpha, then this map is monotonic. What does it mean? It means that if f1 is, so it's like a monotonicity of Riemann-Stieltjes integral. So if f1 is smaller than or equal to f2, and obviously they are from alpha, then the integral of f1 will be with respect to the alpha is less than or equal to a to b. Is So that's a monotonicity. That is the formula. Part C that we would like to prove is that if F is in alpha, the graphic of alpha, and C is some point between A to B. Okay. And we want to compute the integral A to B, the alpha.
Which would be equal to A to
I
C and C.
can basically split it in two parts. C F D alpha plus C to B F D alpha. So that's proving really the elementary properties that you know before, which we kind of taking them for granted actually. Question is the argument for the proof. And B is that if F is for of alpha and obviously F must be bounded. It's like F is integrable, so it's like you need to keep one thing in hand. You know, all this theory works for the bounded functions actually. So, you know, to define a Riemann-Stieltjes integral, you need two things. Number one, boundedness of the function f, and the monotonicity and boundedness of the function alpha. So that's what the minimum requirement is. So if f is integrable, it should be bounded in the first place. So if it is bounded in the first place, then there must be a number for which f of x is less than or equal to m. And we can prove that if this is the case, then the integral from a to b of f d alpha is less than or equal to, give me the guess what should be the case, m times
A B B minus A.
of b minus b, oh sorry, alpha of b minus alpha of b minus so it's like since f of x is less than or equal to m, so you can pull this out of integral, and then you need to integrate what d alpha from a to b. So you're gonna have m times alpha of b minus a. That's what it means. Is. Part E of the integral is that if f interestingly is Riemann integrable with respect to alpha 1, and it is also Riemann integrable with respect to alpha 2. Okay. Then you can ask, can I integrate it with respect to the sum of these two alphas? Okay. In other words, so precise, then f belongs to R of alpha 1 plus alpha 2. So it's like integrable with respect to alpha 1 plus alpha 2. And the integral, since it is integrable, so the question is, what would be the integral of this with respect to the sum? So it should be, as per expected, what should be? F d alpha 1 plus a to b f d alpha 2. Okay. This is what that we would like to prove. In this, add one more. I something. Sorry. F1, F2, alpha belongs to this. Then this sum belongs to R of alpha. Not only sum, but C multiplied by F will also belongs to
Scalar multiples.
scalar multiplier. And I can also add that if you want to integrate CF with respect to D alpha from A to B, then it should be same as C times of D F D alpha. So it's like this Riemann-Stieltjes integral is a linear transformation. Linear transformation from where to where? From vector space
R alpha.
R alpha to
R alpha into R.
R. Real.
So what you call such kind of linear transformations. So it's like we can show actually that R alpha is a vector space. But what should be the field? We know that every vector space is a vector space
Over some field.
or some field from where you choose the constants. Okay. The field is R.
R.
So I have the map from vector space into its field. What you call such maps?
Isomorphic.
Oh, no. What you call such maps? You call linear functionals. So these are functionals. Okay, so it's my question. If you haven't done it, we'll do it afterwards. Such kind of maps are called functionals. So it's like whenever I have a functional on a vector space, it means that it's a linear map from vector space into its field. So this shows the first property shows that integration, Riemann-Stieltjes integration is a linear functional on a space of all integrable. Okay? Good.
Functional.
Linear functional.
Let's move ahead and try to prove some of properties of these.
Yeah. Yeah, precisely.
Okay. So let's begin with part A. And let's begin with the easy task. Okay? So let's see that YCF should be Riemann-Stieltjes integral. Okay. Why this should be the case? So for that, I need to compute UFP. So imagine given epsilon positive. My task is to find a partition for which, the upper Riemann sum and lower Riemann-Stieltjes sum of CF should be less than epsilon. Okay, so what would be UFP alpha? No. Let's see this. So think about it. Since F belongs to R of alpha, so that was his underlying assumption is. So it must be Riemann integrable. So if it is Riemann integrable, so there exists a partition P such that for that UFP alpha minus LFP alpha can be controlled by epsilon. And my claim is that the same partition is going to work for. Why? Just think about it. So you have UF CF P alpha. So this is equal to what? This is equal to sum of capital MI, I equal to 1 to n, and capital I. Now, let's call this C. Let's call it MI, but with respect to C. It's not power C, but I'm just symbolizing it with some. Now, what is this MI of C? It is the Riemann of C f of x such that x is between xi minus 1 and